So first, I would like to thank the organizers for organizing this conference. I also maybe should apologize because I changed the title of my talk because it's going to be a little bit more broad and I also be more speculative somehow. So I'm going to talk about this from microscope loss to microscope behavior. So let's just go to that. So what's the motivation? No, idea is how to get the macroscope behavior we see every day here, no, in our daily lives, from the microscope physics we learn from since the Newton laws and even to the quantum mechanics. No, so the first question, which is an old one, no, is like this equilibrium thermostates, how it happens. No, you have the second law, the error of time. How can I explain this? This is a foundational problem that happens even before we are discussing the foundations of quantum mechanics. People were already arguing about the foundation of statistical mechanics and thermodynamics, okay? And also you have this other motivation, which is this kind of the same question, but in the quantum mechanics, no? How we get the classical world with well-defined properties from the quantum world where you have superpositions, entanglement, and all this, no? So I think this, the main question, which is for in both cases, is to get this microscope physics from the microscope laws, even in classical mechanics or in thermodynamics, no? And also the popular solution for this, no, in both cases, is like I have the environment. I have a thermalization or even the coherence. There are theories where I have some outside environment that is the one responsible for taking me to the classical limit in the decoherence program or to the thermalization. This is one of the, it's not the only one, but it's the most common one, okay? So here I'm gonna make kind of a manifesto, which is my idea of how to tackle this problem. I hope some of you disagree with that. I would be happy to discuss this, okay? Because it's just my political view on this problem, you know, is that a necessary ingredient to do this is that you have to introduce coarse graining in your theory. No, and I wanna say this because many times when I talk with some people, they say, no, it's not fair that you introduce a coarse graining. Everything is so easy. I mean, this is not way. And I'm saying the other way around. I think you have to do that. If you do coarse graining, then you you should not get your classical limit or the thermodynamics. Because what you observe here, it's a coarse grain measurements. We are not having tunneling microscopes to see or walking around with them. They are in the labs just for specific things, okay? And also, that's why I'm telling here. So, and I mean, we should not build a theory that explains things we don't observe, okay? So we know nowadays that you can violate the second law if you have a small system and probabilistic. People do in the lab. So why are you still thinking like Boltzmann and the old people that you wanna have a second law that is valid for any system, anytime? We know already that this is not true. I mean, you observe that the second law is a probabilistic one that only works for a large system. I mean, the probability of violation decreases exponentially as the system size increases, okay? And last, there's a fact also that we see in nature, no, that statistical mechanics use probabilities. I'll tell more about that. And how it works, no, it indicates that the probability distributions you should get in your theory should be very concentrated, okay? So that's I mean, you don't expect to do something else, okay? So that's just remind you what you do usually, no? That's why you should learn your course on statistical mechanics. I hope you did that, but if not, let's try to review a little bit, okay? So usually what you do is that you introduce probabilities. Now, that's the first time maybe in a physics course you learn about probabilities. You're just learning about calculus and differential equations, but then you go to statistical mechanics and you learn that you have to do probabilities. No, sometimes when you're physics, you're very disappointed. I thought this was exact science. What are you doing with probabilities now? No, but you have to do that, okay? Because we have a large system. You always think of a gas. You don't know the positions of all the particles, but you know something. No, you know it's a box. You know it has a certain energy, and then you have your phase space, and you say, okay, that's defined a set of states are the possible microscopic states. Okay. But I don't know which point of this phase space you are, and then I just gonna put, you say something, no? I put by hand the probability distribution here, and I take average. But in the lab, actually, the gas has a well-defined position, at least we believe on that, okay? There is a real state there that's evolving time. Your experiment takes a finite time, and actually what's happened here is that you're making a time on average. It's not ensemble average, it's a average on time. And you know that your theory at the end, it works. No, these two things get you the same results. And the question is why? No, that's the foundational question of statistical mechanics, okay? And one way to justify, so this works, and also what I have to do here is use some kind of probability distribution and sometimes use what you call the microcanonical probability distribution, which is a uniform distribution over all the possible states. And the question is just justify why I have this guy. And there are many ways to do that. One is James principles, where I just get the probability distribution that maximize my entropy or ignorance, if you prefer. And also I can talk about ergodicity and chaos, which say actually that the dynamics is such that I just fill all these states. So I'm just going all around. So that's what one characteristic of chaos is, not the only one, but one of them. But I mean, this has some problems also, because I mean, usually most of the systems are not ergodic. The time scales to do this, they're large, okay? No, I mean, this is a thing, I think this is still like the community, it's a bit divided. Some people think this is the real solution. I will claim that this is not the one, okay? But I have to tell this is a very common one. And the one I will claim is this argument of typicality, okay? What is this about, okay? The idea is that when I go here and look at my phase space, okay? If I look at the microscopic configurations, they are very different. But when I do some coarse graining and look at some macroscopic observables, most of these states look like the same. Okay, this is the idea. And it's a easy way if I have spins, okay, or you can think of a gas that the particle can be on the left and the right, and you can see that there are much more configurations on half of the particles are up and half of the particles are down than when all the particles are up. Actually, there is only one configuration with all the particles are up. There is only n configurations when all are up, less one, okay? But the number of, if you're gonna increase, no, and you approach half, you know that the number of configurations increase exponentially, okay? Actually with a factorial, okay? So that's one way to justify this, and you say that this macroscopic behavior, it happens because it's the typical one. Most of the microscopic configurations look like that, okay? How can I do this in the quantum mechanics setting? Okay, so the idea is, again, I have some restriction, the gas is in a volume, so I have a restricted Hilbert space, okay? And what I can do now, I can postulate the equal probabilities a priori, which is a uniform distribution, is the identity in your subspace, okay? And what, you can do calculations here, okay? Most of the textbooks have just one paragraph about this ensemble, because usually you don't have in the lab a system with a fixed energy. What you have is a fixed temperature. And what you do is that you look at a small system, okay? The rest would be your bath, okay? So in quantum mechanics, you do a partial trace, okay? And this is gonna be the state that describes your system. So it's clear that you start with the probability distribution, or we say you put it by hand, because I don't wanna, I'm not able to make a microscopic description, and then I make a trace because I don't observe the whole system, and I get this. If I have some conditions of weak coupling, I can show that this guy is like the Gibbs state, the canonical one. But it doesn't have to be, okay? That is a particular, it could be the grand canonical one, or it could be anything else, okay? I mean, the whole formalism doesn't depend on that. This is just a particular case. So what's the typicality idea or the argument, okay? The idea is that, okay, I don't know which psi is, but I assume there is a well-defined psi. I'm not gonna put the probabilities by hand on my theory, okay? I'm gonna assume there is a psi, I don't know which one, okay? And then I'm gonna pick one of these psi. And then what I'm gonna do is still gonna make the trace over the rest, okay? And I'm gonna get some reduced density matrix. And the question is, what's the difference of doing this way, the calculation, where you don't wanna assume to use probability, you're like the physics that still believe that you shouldn't use that, okay? And the question is, this is the textbook, and this is the typicality argument, okay? And you're gonna say, if I do this, is my predictions much different than I would get with the textbook one, okay? Because if there are, so the theory is wrong, you know, because we know this works, okay? So the question is there, Of course, this, you say, this is going to depend which psi I got, no, because I just choose a psi. So at the end, you have to somehow introduce probability, because I have to say, okay, I could get this psi or the other one, and I'm going to ask, okay, how many times you're right or close to the right answer, how many times you're far away from that. And to quantify this, you have to use the concept of probability. So we could argue here for the whole day or just after the drinks and the dinner, okay? What's the difference of using probabilities here and probabilities here? But let's assume that, I will claim that this is different. It's just a way to set a volume on a set of states, okay? It's not the same way to use this, okay? So what I'm gonna do is that I'm gonna make an average on the error, okay? I'm gonna pick many psi's, I calculate the error, and I'm gonna quantify how much I'm doing wrong, okay? If this is small, I'm good. And actually, if I use this Haar measure, okay, you can relax this, but it still have to be a kind of very spread measure. It doesn't have to be exactly the Haar measure. You can show this kind of result, okay? I'm gonna show you the reference. This is not mine result. That this average is upper bound by this guy. Here is your average state, okay? I'm picking this, that's psi here. I can average over here, I still get the identity, okay? And I can show that this is given by this, and that this upper bound, which is the Hilbert space dimension of your subsystem, divided by the Hilbert space of the rest, okay, or the total system, actually, the restrict. And usually, so you show that your first system is smaller than the rest, which is the usual setting in thermodynamics or statistical mechanics, okay? You're gonna show that this is exponentially small, okay? So you say that most pure states locally look like thermal. So you can, this is a way to quantify this typicality argument I was telling, is that quantify that most microscopic configurations look like the same, okay? So you say that typically this guy is close to this one, okay? So this actually hit the news in the quantum information community in 2006 by this paper in Nature Physics by Sandhu, Tony Short, and Andres Winter, and they call the principle of equal probabilities a priori is apparent. So he said, this is not a fundamental principle in your theory anymore with this argument. It's just a principle that you can use, it works, but it's not necessary, okay? So the result is like this concentration of measure is a way that mathematicians use to say that some probability distribution just has a concentrate around the average, okay? And the idea here, which I think is one way they really this result quotation, and actually is in the title, the entanglement, the foundation of statistical mechanics, is that the reason I start with the pure state, I trace, and I get something that is mixed and keep it close to a thermal state, this guy has to be the same entropy of that one. But the entropy from this guy comes from the entanglement between it and this and the bath. So it's clear from this way to set this result that entanglement is the responsible for allowing you to have this typicality argument, okay? So, but actually, so there's a bit of history. I like to put the results in context here. This result was 2006, but a bit later, people start to realize that this was actually not old news. Was new, okay, was old news. So, because actually just say, Lebowitz with collaborators also had a PRL at the same time, okay? But actually, and they even claimed that this part of this argument was already in a book by Schrenger. But then people realized, that there was already Gemmer and others that has this quantum thermodynamics. Before we started talking about quantum thermodynamics and have conference on quantum thermodynamics, they had this book where they say a lot of things about quantum thermodynamics, and also most of these calculations on typicality are there. And later, actually, Seth Lloyd, actually in his thesis in 1988, also had most of these arguments. So he reformulates statistical mechanics in terms of pure states. So he was doing the same thing in 88. Actually, at the end, he put the thesis on the archive such that you could cite it and read it easily, okay? And actually, if you also, there is this paper by Physics Today, also by Lebowitz, where he's always showing that, this typicality argument was already proposed by Boltzmann, okay? It's very, very old, okay? When Boltzmann get in trouble with all this paradox about the recurrence of Poincaré and other things. He thought about the way to thinking about these arguments, and he made this typicality argument already, okay? So it is in this paper, okay? And actually, so this is also a nice paper, I just want to say, that tells out this history of why Boltzmann was changing his mind about what was the meaning of probability there. And just to say that actually, then we find out, okay, that this was even made by von Neumann in 1929, okay? If you go to archive now and ask for a search and point the von Neumanns there, you're gonna find that there is a paper by von Neumann in 2010. Because this guy here, I mean, also this group here, they found out this paper by von Neumann, which was still in German in 2010, okay? And they translated it, made some commentary, and posted an archive. And there, most of these typical arguments are there, and much more. There is ATH, and all these quench theorems are already there also, okay? So coming back to typicality now, so this solves everything? Of course not, no, unfortunately, we can't, it's not easy to close a problem, no? So one argument, no, is that it appears to, it's just phi, okay, somehow, because you say there is just a exponentially small set of measure zero in the Hilbert space where things are wrong. So, and you don't need any more chaotic dynamics that fill everything. You just need your dynamics to be outside this set of states, okay, which is exponentially small, and then you could explain the thermal behavior, okay? But one problem is that we also say, this is a folklore, no, it's theorem if you want, that nature doesn't explore the whole Hilbert space. The Hilbert space is too huge, okay? And this is also related to the fact that it's hard to simulate. So usually you say, oh, there is a set of physical states, okay? Like you're gonna exclude all the Schrödinger states that we don't see there in nature. And so you should sample just this small set, okay? And maybe this set has some large overlap with your atypical set, and then your typicality argument is still a nice theorem, but doesn't serve anything for physics, okay? The theorem is still correct, but it's not useful to explain this. So there is some works who try to make this typicality argument in a set of states. So actually, and there is also another problem, what I think is not so much told about, is that even when you have this subsystem and you calculate the reduced density matrix, you have to remember that your subsystem is still a macroscopic system, okay? You have a bath, you have your system, but the system, your gas, is still a macroscope with 10 to 23 particles. And if you want to calculate the reduced density matrix of this guy, it's okay, but it still has too much information. Nobody's going to do a tomography in a gas with 10 to 20 or even 10 to 10 molecules on there, okay? So it still contains too much information. So this is two things that it's open questions, okay, that we should develop. So in this question of to find us a physical state, so I'm just gonna make some propaganda of an old paper we have when you try to make this typical argument in the set of matrix product states that have a area law. This doesn't have entanglement that increase with the volume, and you show that you can still do the typical there. This is a nice set of physical states, I believe. It's not the only one. So Jens also and others have results when you have like a set of states with a fixed energy and other things, or small fluctuations. There are other works. I should cite them. I didn't have time to do that. And so what is the main result I want to present today, which was the original title of my talk, is this typical under general quantum channels. So the idea is I have this set of states, okay, but I'm not gonna get it directly. I'm gonna get these states, okay, there, and then I'm gonna make a channel. I'm gonna make some operation on that. It's gonna do another subspace, okay? And now I'm not gonna have the subsystem anymore. It can be anything. So imagine that instead of making the partial trace, I make something more general, any quantum operation. The partial trace is just a particular case of that, but I could do anything about that, okay? It's like I could even do like this center of mass and relative coordinate systems. I have this generalized subsystem. This is much general, okay? And the question, can I still have typicality on this new subset, and we prove a similar bound, okay? Still, you make the difference between the original textbook and this guy and calculate the average error, and you have an upper bound that depends on the dimension and depends on the entropy of our channel now. And then what you see, what I think is expected, is that if your channel erases a lot of formation, has a large entropy, this bound becomes small and you will recover typicality. So it's a kind of, I would say, very broad generalization, because this channel can be anything, okay? Any CPPT map, okay? So this is the result. I have it with Fernando, which is here, and he's gonna also calculate them. And also other calculators, Pedro, Gabriel, and Raul Valerus, which is also in CBPF, okay? And just to continue a little bit here, I can also do, actually, also almost at the same, a little bit later than the Popescu paper, there was this paper by Peter Reimann, which is typicality not for the canonical ensemble, for the macro canonical ensemble. And the idea now is that I doesn't make a trace, but I make a measurement of some observable, which could still be on the whole system, okay? It can be a global observable because it's a whole system, but usually it's a local one. So there is also this problem with these definitions of local, global in the community of quantum information and condensed matter. So I'd say is the total magnetization, okay, you'd say it's a local one because it's a sum of local terms, but it's like a property of the whole system also, okay? And also you can find a similar bound on this, okay? And also you say that this typical value, the average here, so you have this state minus what you get with ensemble. This is the variance you'd get, and you also show that this is upper bound by this, and now it's appeared the purity of your average state, which usually decays exponentially also, as in the Popescu paper, okay? So most of the states still look thermal, even in the microcanonical setting, okay? If you only have access to some observables. Of course, if I'm able to measure all the possible observables, I'm doing tomography and I'm gonna find out that I have a pure state, okay? And the question is, where is entanglement on this argument? Because the concept of entanglement is not, why is needed here? It's not clear anymore. So I think this is also a question that recently we tried to address. And what you did on this paper that is still archived, okay, with also Pedro and Gabriel, is to make this typicality now just using a set of states that is key separable, okay? So I have any particles and I divide it in blocks, and these blocks are separable, so the entanglement is just inside the blocks, okay? This is a very common set of states that you use to study entanglement. And if the number of blocks is equal to the number of particles, I have completely separate states. If k is 1, I have a completely entangled state. And I can still deduce a bound, okay? And now, if I have qubits, just to make it easier, I still have this 2, 1 over 2, and in exponentials, they're n over k. So if I increase my system size n, keeping the blocks fixed, I'm increasing the amount of entanglement in your system because the size of the blocks are increased. So I have more and more multipartite entanglement somehow, I'm allowing. And then I see an exponential decay, okay? But if I increase n, and I also increase the size of the blocks, I'm keeping the type of multipartite entanglement fixed, I don't have the exponential decay anymore. I just have a power law here, 1 over n, okay? So I still get typicality, but not exponential decay anymore. But if you go back to your textbook statistical mechanics, you're gonna remember that from the law of large numbers, what you can prove there is that the fluctuations, the relative fluctuations, goes with 1 over square root of n. So if I wanna reproduce thermodynamics, I don't need exponential small fluctuations. I only need 1 over square root of n. And what I'm showing here that even if I have a separable state, I'm still able to get that. So the idea is that the entanglement is not needed to explain the macroscopic world we see, because you can already get this square root of 10. But we know in our quantum labs, with ions, 10 ions, 50 ions, or Josephson junctions, you also have a lot of experiments where you see that you have 10 ions, I make a quench, and I see this guy thermalizing and equilibrating. Why is that? So to explain that, I need this exponential decay, and then I did entanglement. So the idea is that to entanglement is necessary to explain this thermalization in small quantum systems, but not in the classical world. Okay. And finally, this is just a graph to show that the boundaries somehow work. So just to speculate, now I think that this typicality argument can also somehow explain, maybe it's another way to explain the quantum classical transition, because usually the typical state is kind of thermal and classical. I'm not going much on that. And actually part of these arguments in some more house, we develop more with Fernando and also the other collaborators. And that's what he's gonna talk in the next one. So stay put here, you don't have to move to hear more about that. And I think this is all. So conclusion is that typicality can explain the emergence of equilibrium thermal behavior. MESA also can help to understand the quantum classical transition. And just to show you that, I mean, Natal is very nice. I like it here, been here many times, but Rio is also nice, okay? So this is Niterói. Actually, we are not in here. This is, they say we have the Rio, that's Rio, and you are here in the other side of the bay, and you have a quantum information group, it's a large one, okay, with many people, and also you're welcome to visit us, okay? And thank you.
Thank you for a nice talk. We have time for maybe 1 or 2 short questions. Okay, I maybe have one. Please. Okay, I have one quick question about maybe your last result about like sort of limited entanglement. Can you move back to the slide? Yeah. So, what class of observables you look at? Because I'm a bit puzzled.
No, it's still local observables. This only happens. So I was quickly. So this is only true for local observables. There are some of terms that have a finite
support.
Support. Yeah.
Okay. So like,
if I have a completely any point correlation, this does not happen. Yeah.
I see. So like, for example, if k equals to n, you still have like decay.
Yeah. For local observables.
I see.
Yeah.
Thanks.
Just for local observables, yeah.
Okay. Nice talk, Thiago. Okay, so you say that when you randomly sample the Hilbert space and do that operations, you typically get very close to the thermal state, right? But about how you fluctuate from this thermal state. So is it typical that the states have some remanent coherences, or you have only fluctuations between the Maxwell-Boltzmann probabilities? You know, my question is, have you seen how is the detailed behavior of the small deviations from the equilibrium state?
So actually, this bound here is upper bound the variance. I'm not sure if I understand.
No. It's before this.
But I mean, at the end, we're just bounding the variance, no?
The first one. Yes, this. So
yeah.
So you have rho s very close to the equilibrium state. But how? I mean, are most of the rho s incoherent, or do you have some coherences?
I would say they're incoherent because they are close to. It depends.
No, you can have small coherences.
Yeah. I mean, they're close to a thermostat. So the question if the thermostat has some coherence or not, that's going to depend on the temperature. So, but I mean, they are close in the sense of the trace norm here. Okay, so it's a real distance for operators. So I'd say most of these properties are close. Okay, so it's going to depend. I think if this omega state is a has not much coherence at the end.
Okay, we talk later.
Sure.
Okay, let's thank the speaker again.